Hey, good afternoon, and welcome back to Super Embarrassing Cringy Chemistry Videos, Volume 2. Um, so last time we went over your notes for how to determine excess reactants, how to figure out how much of your excess reactant was reacted and how much was left over. So I thought for this video, I would like to go over the practice problems that you had to go with it, and I thought while we're at it, we might as well go ahead and do the study guide you were assigned as well as the answers for the lab that you guys did or watched on a video. But before we do that, real quick, I just want to remind you guys, like, I know Andy's on at 5 and I'm not trying to encroach on his territory, but make sure that you're taking care of yourselves. I know that for me, there are some days when I get up early and I'm super motivated and I have breakfast, and then somebody else gets up and cooks and I have a second breakfast, like today. There are some other days where I get so busy I don't eat until 6 o'clock in the evening, to be honest. There are days that I go to bed at 10, and there are days that I wake up at 4 in the morning on the couch and have no idea when I fell asleep there. So I think it's just important for all of us to try to remember to get back into a routine, because I don't know if you guys are like me or not, but it's been messing with my head. So I might try to do something like that. I think it'd be good for you guys to do that too. Um, and also, one more thing, I'm going to try to put timestamps in the description box. So if you want to skip things like my super sappy speech, you could do that. Or if you want to go straight to the worksheet, straight to the study guide, or straight to the lab, you can also do that. Um, One more thing before we start. You guys, not that I can enforce it or anything, but I'd really rather you try these on your own before you watch the rest of this video, because otherwise it's basically like cheating. This is just to help you so you can check yourself and so that you know that you're setting everything up the right way. The first few I might go over a little bit slow, and then I might try to speed up just because this is going to end up being a long video. But let's start with the practice problems you guys were given. This first one, a few people have already contacted me about some problems on this, and the first one is deceptively simple. So if you look, it asks you if you have 2.34 moles of 10,4 good buddy chloride. Sorry about that, my dad's a truck driver. And you react that with 4.36 moles of sodium. If you react every bit of it, it wants to know what the maximum number of moles of tin that you're going to get. And that is going to depend, of course, on your excess reactant and your limiting reactant. Like, basically, which one are you going to run out of first? The people that have reached out to me, I told you I don't care a bit about the word equation, but I'm going to go over it with you anyway. So we know that when react 10,4 good buddy chloride, and I promise I'll stop that joke, reacts with sodium, you get sodium chloride and tin. And so now we need the formula equation for that. And this one is obviously way more important because you need to balance it so you know what coefficients to use when you use your mole ratio later on. And for that, we start with the tin-4 chloride. And we know that the tin-4 has a +4 charge because that's what that Roman numeral is going to tell us. And chlorine always has a -1 charge. So we need 4 chlorines to balance out the charge of the +4 tin. And I'm not going to put coefficients yet, but that's going to react with sodium, which is just a plain old metal. It's not one of the diatomic gases that we have talked about before. And your products, you're going to have sodium chloride. Sodium has a +1 charge. Chloride has a -1 charge as always. And plain old tin metal. Okay, and so now we need to balance it because those coefficients are important. And for this one, where I would start is to look at this chlorine, because that chlorine, you have 4 of them, and you need to have 4 chlorines over here. So the only way to do that is to add a coefficient in front of the sodium chloride. And so now you have 4 sodiums over here, so you add a coefficient here. Now you have 4 sodiums on both sides, and it is balanced because you have 1 tin, 4 chlorines, and 4 sodiums. So, like I said before, we're trying to figure out the most amount of tin we can get before we run out of one of our reactants. And the way we do that is basically doing the same stoichiometric calculations we've done before, but we're going to do one for each reactant. So we want to know the most we can get if we react every bit of our tin 4 chloride, and the most we can get if we react every bit of our sodium. So let's go ahead and start with tin 4 chloride, so it's going to be easy. And you don't have to do this pathway thing I do, but I know some people find it kind of sort of helpful. But we know we're starting with moles of tin 4 chloride. Sorry, somebody's at the door, I think. Okay. And we're trying to get from moles of tin 4 chloride to, sorry, my kids keep coming in here, to moles of tin. So this one is going to be really simple. It's one step. All you're going to need is the mole ratio, or the mole rat, because you know I like to abbreviate. So let's start with 2.34 moles of tin 4 chloride. And now we just need the mole ratio. And we know that for every 1 mole of tin 4 chloride, we need, or we don't need, we'll get 1 mole of tin. And the tin 4 chloride goes on the bottom so that these can cancel out, and that leaves us with moles of tin. And since this is a 1-to-1, there's really nothing to type into your calculator, so we know that we're going to get 2.34 moles of tin produced if we react all of the tin 4 chloride that we have. But we don't know for sure yet that it's even possible for us to get that much tin, because for all we know, we could run out of sodium first. And that's definitely a possibility, because if you see here, for every 1 mole of tin produced, you need 4 moles of sodium. So, like, if you just think about it, that's going to be something that's really, really easy to run out of. So just taking a glance at it, that's the one I would guess you would run out of. But anyway, so if you want to do a pathway again, we're trying to go from moles of sodium to moles of tin, and all you need is the mole ratio. Again, very easy, one step. I'm going to try to make it take up a little bit less horizontal space this time, but we know that we have 4.36 moles of sodium, and we know that for every 1 mole of tin that's produced, we need 4 moles of sodium. And so moles of sodium cancel out. If you type that in your calculator, it turns out that you can get 1.09 moles of tin that can be produced. And so now we just compare these two numbers. So we know that if all of the tin 4 chloride reacts, we can get 2.34 moles of tin. But we also know if all of our sodium reacts, we can only get 1.09 moles of tin. So what that means is that we are going to run out of sodium first. So sodium is our limiting reactant. And that means too that since this is the lower number, this is the most amount of tin that can be produced from this reaction if you have this amount of your reactants. Okay. Alright, so let's move on to the next one. We'll try to get through the next ones a little bit faster than that one. Okay. Ugh. Alright, so now what we've got is 13.5 liters of nitrogen, and that's going to react with 17.8 liters of hydrogen at STP, which frankly from what we know we can usually assume, and we're trying to figure out how much ammonia can be produced. Okay, so we're going to do that problem the exact same way because we're basically trying to figure out the same thing. We're given a certain amount of both reactants and we're trying to figure out how much product we can get. This one is a little bit different and it has more steps just because instead of moles it's giving you liters, and it wants you to go from liters, which is the unit of volume, to the mass of the product. So it's a little bit hairier than the other one. But it does give us a balanced equation, so that's going to save us a little time. So let's go ahead and start with nitrogen gas. So just to show our pathway, we're going from liters of N2, because that's diatomic, and we also know that because it gives us that in the equation. We're trying to go from liters of N2 to moles of N2, because we need to go from moles of N2 to moles of our product, which is NH3. And then what we're ultimately looking for is mass of our product, so then we need to go to grams of NH3. And to go from liters of N2 to moles of N2, we need the molar mass. To go from moles of N2 to moles of NH3, we need the mole ratio. And to go from moles of N3 to grams of NH3, we need the molar mass. Okay, so let me scoot that over. Alright, let's go ahead and start, like I said, with the nitrogen. So we know we have 13.5 liters of nitrogen gas, and we're trying to go from that to moles of nitrogen. And oh, actually, told you wrong. You need molar volume, not molar mass. Hang on just a second, my kids are at the door. Okay, yeah, I told you wrong a minute ago. We need molar volume. My bad. So. Alright, so molar volume, if you guys remember, no matter what the gas is going to be 22.4 liters per mole. And since we have liters on top here, we'll put our 22.4 liters on the bottom and moles on the top. So now liters of N2 cancel, and we have moles of N2. So now we need to go from moles of N2 to the mole ratio, and for that we need the coefficients from our balanced equation. And since moles of N2 is on the top here, it needs to be on the bottom here, and it has no coefficient, so it's just 1. And for every 1 mole of N2, 2 moles of ammonia, or NH3, are produced. So now moles of nitrogen are canceled. And the last step, we need to go from moles of NH3 to grams of NH3. And for this, we do actually need the molar mass. And just to save you some time, we're going to go ahead and say that's 17.04 grams per mole. Now I like to keep my units and whatever the formula is of what I'm talking about the whole way through, because that helps me keep track. Because you have problems like this where you have multiple substances in the same expression, and it just keeps me from getting confused, and it's just a good habit to make. So if you go ahead and type that in your calculator, you know that if you react all 13.5 liters of nitrogen gas, you're going to get 20.5 grams of ammonia. Okay. Now it's like we said before, we don't know for sure that we can get that much ammonia because we might run out before that ever happens. So we need to find out how much ammonia you can get if we react all of our hydrogen gas. And I'm not going to do the pathway because it's pretty much the same except with hydrogen and because we're running out of room. But we know that we have 17.8 liters of hydrogen, and we need to go from liters to moles, so we're going to use the mole ratio just like we did before. Liters of hydrogen are canceled. And now the mole ratio. So this one is where it gets a little bit different. And just a reminder too, the only time you don't use 1 mole in a calculation is when it's the mole ratio. So just make sure you're only doing that one time. But moles of hydrogen are on top here, so they need to be on bottom here. And we know that for every 3 moles of hydrogen, 2 moles of ammonia are produced. And so now moles of hydrogen are canceled. And the last step is to go from moles of ammonia to grams of ammonia, and the molar mass is going to be the same, so it's the exact same last step as last time. Okay, and if you type all that in, turns out you can get 9.03 grams of NH3. And as always, we go with the lower number because that means that before we can get 20.5 grams of ammonia, we're going to run out of hydrogen. So when we run out of hydrogen, we're going to have 9.03 grams of ammonia. So it's looking for the mass that's going to be produced. That's going to be 9.03 grams. Okay, so last, let's go to number 3. Or not last, we still have 2 more after this, I think. Alright. So now this problem has a different reaction. So you know that if you have 3.18 times 10 to the 23rd atoms of iron, whoa, and that's reacting with 67.2 liters of chlorine gas. Sorry about that focus. At STP, whoa. It wants to know how many grams of iron 3 chloride can be produced. Alright, so this one, oh my gosh, focus. It'll focus when my hand's over there. Alright, so this one, you start with number of atoms for iron, but it gives you liters for chlorine gas. And that's totally fine because with either one of those you can go to moles. And so I'm going to show you the pathway for both of these before I do it. But let's go ahead and start with atoms of iron. So we know how many atoms of iron we have, and we need to go to moles of iron. And for that, we need Avogadro's number. Okay, and so we need to go from moles of iron to moles of iron 3 chloride because we're trying to figure out how much iron 3 chloride we can get from this problem. Okay, and for that, we're going to need the mole ratio. And then last step is going to be to go from moles of iron 3 chloride to grams of iron 3 chloride. And for that, we need the molar mass. Okay. And yeah, ignore that number 4 down there. Alright, so let's start on iron. So we know that we have 3.18 times 10 to the 23rd atoms. And we need Avogadro's number because we need to go from atoms to moles. And y'all know Avogadro's number is 6.022 times 10 to the 23rd atoms per mole, and that needs to go on the bottom because atoms is on the top here. Okay, so now atoms of iron is canceled, and now we need the mole ratio to go from moles of iron to moles of iron 3 chloride. I'm sorry, this one is really focusing terribly. Okay, so moles of iron is on top here, so in our mole ratio, it needs to be on the bottom. So in the equation, for every 2 moles of iron, you get 2 moles of iron 3 chloride. So that one's real easy. It's basically a 1-to-1 ratio. Well, it is a 1-to-1 ratio. So moles of iron cancel out. And last, you just need the molar mass of iron 3 chloride, which is 162.20 grams per mole. Okay, and if you type all that in your calculator, turns out that you can get 85.7 grams of iron 3 chloride if you react all the iron that you start out with. And I hope you guys can see that okay, because I realize it's super cluttered and cramped. So the next one, when we do chlorine gas, it's a little bit different. This is going to be just like we did in number 2, where we start with volume and we're trying to go to mass. So we're going from liters to moles, well, liters of chlorine to moles of chlorine to moles of iron 3 chloride to grams of iron 3 chloride. And we pretty much already know how to do that. So let's see, we start with 67.2 liters of chlorine gas, and we need the molar volume to get to moles of chlorine. Doesn't matter what the gas is, molar volume is pretty much the same. And so we know it's 22.4 liters per mole, and liters need to go on the bottom. So liters cancel. And now I need to go to moles of iron 3 chloride, and we know that for every, 3 moles of chlorine, you get 2 moles of iron 3 chloride. Okay, so moles of chlorine cancel. And now you need the molar mass of the iron 3 chloride again, which is the same. So it's 162.20 grams per mole. Okay, so now moles of iron 3 chloride cancel, and you get 324 grams of iron 3 chloride from reacting all the chlorine you have. And as always, we're going to go with the lower number. So it turns out, in this case, iron is our limiting reagent because you can only get 85.7 grams of iron 3 chloride before you run out of iron, so you can't get 324 grams. Alright, so let's move on to number 4 and 5 real quick. Yeah, this is number 4, believe it or not, even though I totally printed it off wrong. But now we are looking for, whoops, focus. Okay, so we're reacting 57 grams of potassium with 199 grams of chromium 2 bromide, and it wants to know from that what mass of chromium can be produced. And it gives us a balanced equation. So it wants to know what mass can be produced, but it also wants to know what the excess reactant is and how many grams of it are going to be left over. So it's going a little bit further than the other problems we've done so far. Focus. Okay, so let's start with the chromium. Okay. Let's start with the potassium. So we know that we have 57 grams of potassium. And we're trying to get to the mass of chromium. So we need to go from grams of potassium to moles of potassium, and then to moles of chromium, and then to grams of chromium. So first we need the molar mass of the potassium, which is going to be 39.10 grams per mole. Okay, and grams go on the bottom since they need to cancel out. And so now we need to go from moles of potassium to moles of chromium. And so we need the mole ratio. And we know that for every 2 moles of potassium, only 1 mole of chromium is produced. So now moles of potassium cancel out. Now we need to go to the maximum, or not the maximum, but the mass of chromium that can be produced if all of your potassium is reacted. So we need the molar mass of the chromium, and that's going to be 52.00 grams per mole. And grams go on top since we have moles on top here. Okay, so moles of chromium cancel out, and if all of your potassium reacts, you can get 37.9 grams of chromium. Okay, and again, we don't know for sure if we can get that much chromium. We could run out of chromium 2 bromide before that happens. We don't know. So let's go ahead and figure out how much we can get if we react all 199 grams of chromium 2 bromide. And we start out with a lot more chromium 2 bromide with potassium, but that doesn't necessarily mean that that's going to be in excess, because obviously they have different molar masses. So let's start with that. Grams need to be on the bottom with the molar mass, and the molar mass of the chromium 2 bromide is going to be 211.80 grams per mole. Okay, so grams, chromium 2 bromide cancel, and now we need the mole ratio. So we know that for every 1 mole from the equation, because there's no coefficient of chromium 2 bromide, we get just 1 mole of chromium. So that's a 1-to-1 ratio. So now moles of chromium 2 bromide cancel out. We need the molar mass of the chromium again, which is 52, just like it was in the one with the potassium. So moles of chromium cancel out, and if you top that in, you get 154 grams of chromium that can be produced. Alright, so at this point we can figure out that potassium is going to be our limiting reactant, and the chromium 2 bromide is going to be our excess. But we also know that the maximum mass of chromium that's produced is going to be 37.9 grams of chromium because we're going to run out of potassium before we can get 154 grams of chromium. They're not 154. I was looking ahead. Actually, it's 48.9. Yeah, sorry that happens. My little form that I pre-did over here is a little bit cluttered too. So now we know how much can be produced. We also know that our excess reactant is going to be the chromium 2 bromide. And our potassium is our limiting reactant. Okay, so now we just want to know how much of our excess reacted, because we want to know how much reacted and how much was left over. Okay, so to figure out how much of it reacted, we can start out with figuring out how much of the chromium 2 bromide reacts with the amount of potassium that we had. Like basically, what's the exact amount of chromium 2 bromide you need without having any left over to react with 57 grams of potassium. And I hope that makes more sense once we actually go through the calculations, which we have seen this in our notes. But so we're going to start with 57 grams of potassium. And from there, we need to go to moles of potassium, just like we did before. Okay, so grams of potassium are going to cancel out. And so now we need to know how many moles of potassium reacted, and we need to know exactly how many moles of chromium 2 bromide we would need to react with that exact amount of potassium. And so we know for every 2 moles of potassium, we need just 1 mole of the chromium 2 bromide to react with it. Okay, so now moles of potassium cancel out. And last, we know how many moles of chromium 2 bromide we need to react with that exact amount of potassium, and we want to go to the mass that we need. And this is, I think, where I got tongue-tied before. But we know the molar mass of the chromium 2 bromide is going to be 211.80 grams per mole. And the moles cancel out, and so this is where we get 154 grams of CrBr2. And that's how much of it actually reacted before we ran out of potassium. So this is part of, let's see, yeah, so we're trying to figure out how much is left over. We know how much reacted. This isn't one of our final answers. Alright, so we know how much reacted, and we know how much we started out with. So to figure out how much is left over, all we got to do is subtract. So we know we started with 199 grams of chromium 2 bromide, and we subtract the 154 that reacted, and from there we get 45 grams of chromium 2 bromide that are unreacted. Okay. So this is how much is left over. Okay. So let's see. Basically our final answer, it's looking for the mass of chromium to be produced, and that's the 37.9 grams. And it wants to know which one is excess, and chromium 2 bromide is the excess, and how many grams are left over? It's going to be 45 grams left over. And we have just one more of these, and we'll move on to the study guide. Yeah. Alright, so now we want to know how much butane we can get if we react 13.45 grams of carbon with 17.65 liters of hydrogen gas. Alright, so this one is very familiar. It's a lot like the ones we've done before, and it wants to know which reactant is excess and how much is left over. Okay, it's like I've been doing these for a long time. It still helps me to go through the problem and mark up what I know and what I'm trying to find, just because I can like keep track of my thoughts better. But it gives you the balanced equation. So let's start with carbon. So we know we have 13.45 grams of carbon, and we need to go to moles of carbon. And so for that we need the molar mass of carbon, okay, and we need to go from moles of carbon to moles of butane, and we know that for every 1 mole of butane, which is C4H10, we need 4 moles of carbon. And then we need the molar mass of butane, which is, well, we don't need the molar mass, we need the molar volume because we're looking for a volume of butane. So that's 22.4 liters per mole. Okay, and so from that, we know that we can get up to 6.271 liters of butane if we react all 13.4 grams of carbon. Okay, so now let's go over to hydrogen. So we know that we have 17.65 liters of hydrogen gas. Whoopsie. And we need to go to moles of hydrogen. So again, it's a volume, so we need the molar volume. So for every 1 mole of hydrogen gas, you get 22.4 liters at STP. And then we need to go to moles of butane. And for every mole of butane to be produced, you need 5 moles of hydrogen gas. And so moles of hydrogen cancel, liters of hydrogen cancel, and again, we're trying to figure out the volume of butane, so we're just going to go right back to the molar volume. So for every 22.4 liters of butane per mole, and that cancels, and you can get 3.530 liters of butane for every 17.65 liters of hydrogen that you react. And so in this case, it turns out that our limiting reactant is hydrogen. So the most that can be produced is 3.530 liters before you run out of your carbon. And so now, again, we need to figure out how much of our excess reactant actually reacted. And so since our limiting is hydrogen, we know that carbon is our excess reactant. And that's one of our answers. So I'm going to put that in a square. So carbon is excess. And we need to figure out how much of that carbon actually reacted so we can figure out how much was left over. And so we need to know the amount of carbon that reacts with the amount of hydrogen that actually reacted, since we know that all of the hydrogen reacted. So we have 17.65 liters of hydrogen. We need to go to moles just like we did before, using the molar volume. And liters of hydrogen cancel out, and then we need the molar or the mole ratio, and we know that for every 5 moles of hydrogen that reacted, there's 4 moles of carbon that reacted. And so moles of hydrogen reacted, or moles of hydrogen are canceled. And we want to know how much carbon reacted, and we start out with carbon, and we have its mass because it's a solid. And so we're going to use grams instead of liters because, frankly, we don't have carbon as a gas in this case. So we need the molar mass. So the molar mass of carbon is going to be 12.01 grams per mole. And when we figure all that up, turns out that 7.517 grams of carbon reacted with the hydrogen to make the 3.530 liters of butane that we got. And so now we want to know how much was left over. And so we know we started with 13.4 grams of carbon, and we know that of that 13.4 grams, only 7.517 grams reacted. And so it turns out we have 5.879 grams of carbon left over, or since it's subtraction, these are not significant, so 5.8 grams of carbon are left over. Alright, so let's make sure we have all parts of the answer that we need. So what volume of butane can be produced? We know that's 3.530. Which reactant is excess? We know that's carbon. And how much of it is left over? We have 5.8 grams of carbon left over. Alright, and if you have any questions about any of that, you can leave them in the comments or send me an email. But let's go on to our lab. Now, since you guys were not able to do this in person, I went ahead and gave you numbers to work with. And so since everybody has the same numbers, everybody watched the same video, everybody's calculations should be more or less the same, and everybody's observations also, since you guys watched the same video. But basically, as much as I want full sentences, what happened was you had a clear solution, and that's my abbreviation for solution, and another clear solution, and you got a yellow precipitate. And a precipitate is just a solid that forms from a reaction that comes out of solution. So it is not soluble in the conditions that it's in. It's not soluble in the water that it was dissolved in, like the reactants were. So it comes out of solution, becomes a solid, and it precipitates down to the bottom of the test tube or beaker or whatever you happen to be mixing it in. And the word equation, we know it was lead to nitrate, and that reacted with potassium iodide. And from that you got lead to iodide and potassium nitrate. And what happened here was a double replacement or double displacement reaction. So here you started with lead 2 and nitrate, and those were together. Potassium and iodine were together. And so if we follow those, you have the lead here and the nitrate here. So they split up, and you have the potassium and the iodide here. So the nitrate and the iodide switched places, and you started with 2 compounds, you got 2 completely new compounds. And the balanced equation for that, so we have a lead with a +2 charge, and nitrate has a -1 charge, and so you need 2 nitrates to balance out the +2 charge of the lead. And that is aqueous because it's dissolved in water. So that's what it meant when it said include symbols. It wants you to include like what state it's in. And that reacts with potassium iodide. Potassium has a +1, iodine has a -1, and that is also aqueous. It's dissolved in water, and that is going to produce lead 2 iodide, and we need 2 iodides to balance out the lead. And if you look at your solubility rules, it turns out this is the insoluble compound, so this is going to be your precipitate. Another way that we write that sometimes you'll see it with an S, sometimes you'll see it with a down arrow, and that just means that it precipitated out of solution. And with that, you're going to get potassium nitrate, and that is going to be aqueous. And then we just need to balance that. So you need a 2 here and a 2 here, and you are all set. Oops. Okay. So next is the theoretical yield, and that's just going to be what you expect to get if, if all of your limiting reactant actually reacted. And so from the numbers that you're given at the top, I guess I can go back to those, these, and that's the last time I'll do that. So from the numbers you're given at the top, you know that you have 3.21 grams of lead nitrate, okay, that you started out with. And we need to figure out how much of the lead 2 iodide can be produced when you react all of that lead 2 nitrate. And so first we need the molar mass, which is going to be 331.22 grams. I'm going to save some space here and not write out that formula per mole. So grams cancel here. You need to go from moles of the lead 2 nitrate to moles, of the lead 2 iodide. And from the equation that we balanced right above this, we know that it's 1 to 1. So for every 1 mole of the lead 2 nitrate, you produce 1 mole of the lead 2 iodide. So moles of lead 2 nitrate cancel. Now you need the molar mass of the lead 2 iodide, which is 461 grams. Oh, can you see that? Per mole. And if you type that all in your calculator, you get 4.47 grams of lead 2 iodide. And we don't know for sure yet if this is our limiting reactant because we haven't calculated how much we can get if all of our potassium iodide reacts. So let's go ahead and do that. So we had 3.60 grams of potassium iodide, and we need the molar mass so we can figure out how many moles of potassium iodide we had. And that's 166 grams per mole. Then we need the mole ratio, which we get from the balanced equation. So we know that for every mole of lead 2 iodide that's produced, we need 2 moles of potassium iodide. And now we just need the same molar mass we used before to figure out how many grams of potassium iodide we are going to get. And from here, you can get about 5 grams of potassium, or lead 2 iodide, if all of your potassium iodide reacts. And so turns out that we're going to go with the lower number. So your limiting reactant, or the one you're going to run out of first, is going to be the lead 2 nitrate. And so the most that we're going to be able to get of the lead 2 iodide is 4.47 grams. And again, since everybody had the same numbers, everybody should have that same theoretical yield. And again, theoretical yield or theoretical amount is just how much you expect to get if everything, or if at least all of your limiting reactant gets used up. Alright, so now the experimental mass of the lead 2 iodide is going to be, that's just going to come from the mass of your filter paper and your dry precipitate. So that's like after you do it all and you put it all in the filter paper, get rid of all the liquid, dry it out, how much the filter paper and the precipitate weigh together. And so all together, they're 5.72 grams. And you need to subtract the mass of the filter paper to see what is just the precipitate. So the filter paper, since we totally got the mass of that too, is 1.40 grams. So the mass, the experimental mass of the lead 2 iodide you actually got was 4.32 grams. Okay, so that's pretty easy. And percent error, we didn't go over this. I heard from a couple people asking how to figure this out. This is basically just the difference between what you got and what you expected to get. And like, it kind of tells you how close you were to what you expected. So it's not necessarily how much you messed up, it's just how far off you are from what you expected. And so the way we're going to do that, you have the 4.47 that you expected to get, and from that you subtract the 4.32 that you actually got, and we go ahead and do the absolute value of that because sometimes it's going to be a negative number and we don't need that, and you divide that by what you expected to get, which is 4.47, and you multiply that by 100, and so our percent yield is going to be 3.47%, which is really pretty good. That's not far off. Okay, so now we're going to do the same thing with our lead 2 iodide. Okay, I don't remember what I said. That was percent error, not percent yield. The percent error is how far off you are. Percent yield is how much you got compared to how much you expected to get. So this is going to be a totally different thing. So you want a low percent error and a high percent yield. I got mixed up in my head. But your percent yield is going to be how much you actually got. So 4.32 over how much you expected to get, and you multiply that by 100, and you got 96.6% of what you expected to, which again is really good. 96.6 is an A. And so in number 7, it just wants you to explain why you didn't get exactly 100%. So this could be pretty much anything. It could be that some other reaction was happening on the side because maybe there was some kind of contaminant in the container. We don't know. It could be that some of your product got through the filter paper. It could mean, like, if it had been higher, it could mean that it wasn't totally dry, just anything like that. And number 8 is just improvements. So that could be like making sure your glassware is clean. It could be getting a filter paper that's not going to let as much through. It could be rinsing it multiple times. Just, there's a lot of different things that you could use for these. So if it sounds about right, you'll be fine. Okay, and last, let's go to the study guide. So this is the big one. This is the one that I've heard the most concerns from people. Okay, so let's start with number 1. So we want to know how many moles of calcium nitrate will react with 4.55 moles of chromium 3 sulfate to get calcium sulfate, and chromium 3 nitrate. So this isn't limiting an excess, this is just like if you know that you have 4.55 moles of chromium 3 sulfate, how many moles of calcium nitrate do you need? And this one went ahead and gave you the balanced equation. So this one will be pretty simple. Whoops. Okay. Alright, so you know you have 4.55 moles of chromium 3 sulfate. And you also know from the equation that for every 1 mole of chromium 3 sulfate, that produces 3 moles of, 3 moles of, I got brain farted, 3 moles of calcium nitrate are going to react with it. And so from that, moles of chromium 3 sulfate cancel out, and you know that if you have 4.55 moles of chromium 3 sulfate, you're going to need 13.7 moles of calcium nitrate to react with it. Alright, so that one's not too awful bad. And we're going to kind of zip through these because there are a few earlier on that we've spent quite a bit of time on. Alright, so next, it wants to know how many moles of zinc are going to be produced when you react 13.2 moles of copper with lots and lots of zinc acetate. Now, this is something that we haven't really seen exactly this way before, but basically what it's saying is if you have all the zinc acetate you need, what's the most amount of zinc that you can get when you react 13.2 moles of copper? So when we balance that, let's start out, okay, so we have 2 acetates here. So we want to have 2 acetates here. Now we have 2 coppers here, we want to have 2 coppers here. And so now that makes it balanced. And this one, it sounds harder than it is, but essentially you know that you have 13.2 moles of copper. And you also know that for every 2 moles of copper you have to react, you're going to get 1 mole of zinc. And it turns out that's all you have to do because it just wants moles of zinc. So if you type that in, you're going to get 6.60 moles of zinc produced. Easy peasy. Alright, so now let's go to number 3. So we need to know what mass of gallium chloride is going to react with excess fluorine, so basically all the fluorine that we need to get 78.9 grams of chlorine. And it gives us the balance equation on this one. Whoops. Focus. That's better. Alright. So in this one, we know that we start out with 78.9 grams of chlorine. Okay. And we need to go from grams of chlorine to moles of chlorine, so we need the molar mass. So that's going to be, let me look, 70.90 grams of chlorine per mole. Grams of chlorine cancel. And then we need to go from moles of chlorine to grams of the gallium chloride. So we know that for every 3 moles, whoops, let's see. Oh yeah, and I just realized I'm totally brain farting. So this one is a little bit weird because we're starting with what is produced. So we know that we're producing 78.9 grams of chlorine, and we're going to end up with however many moles that turns out to be. And so we know that for every 3 moles of chlorine that are produced, we need 2 moles of the gallium chloride. Y'all, it's been a long day. Okay, and so now we need to know what mass of gallium chloride we need in order to get all this chlorine. And so we need the molar mass, which is going to be 176.07 grams per mole. And moles of gallium chloride cancel, and so turns out we need 131 grams of the gallium chloride to produce 78.9 grams of chlorine. Alright, so let's whiz right on to number 4. Oops. Let's let it focus. Let's see. Alright, so now this one we have a decomposition reaction. So in this one we have only one reactant and we have 2 different products. So it wants to know, how much ammonium carbonate are needed. Oh my gosh. Come on. I want to hurry. Okay, are needed in order to produce 6.52 grams of CO2. And ammonium oxide is the other product, but we really don't care about that at this time. And it doesn't balance it for you, but as it turns out, it's already balanced. There's 2 ammoniums, and in addition to that, there's 1 carbon and 3 oxygens. So that is already balanced. Alright, so we know that we're trying to produce 6.52 grams of carbon dioxide. And we need to go to moles of carbon dioxide, so we need the molar mass. And the molar mass of the CO2 is going to be 44.01 grams. Then we need to go from moles of carbon dioxide that we're producing to moles of ammonium carbonate that we need. And just to save some space, we know that's a 1-to-1 ratio, so I'm not going to worry about writing out the rest for now. And then we need the molar mass of the ammonium carbonate. So that's going to be 96.11 grams of NH4 2CO3 per mole. And that cancels, and that imaginary thing cancels. And so it turns out that we need 14.2 grams of ammonium carbonate in order, to produce 6.52 grams of carbon dioxide. Alright, let's keep it moving. Alright, so now we want to know, you know what, I'm going to leave this here. Alright, now we need to know the volume of nitrogen that we need to react with 37.2 grams of magnesium to produce magnesium nitride. So it doesn't give us the balanced equation on this one, but we have 3 magnesiums here, so we need 3 here, and that's pretty much all you need to balance it. Alright, so we know that we have 37.2 grams of magnesium, and we're trying to get to the volume of nitrogen that we need in order to react with that. So first we need the molar mass of magnesium, which is 24.31 grams per mole. And grams are going to cancel out. We need to go from moles of magnesium to moles of nitrogen. And so we know that for every 3 moles of magnesium, you need 1 mole of nitrogen gas to react with it. And now we need to know the volume of nitrogen gas that we need. So for that we need the molar volume, which is 22.4 liters per mole. So moles of nitrogen cancel out, and after we top in all that, you need 11.4 liters of nitrogen to react with 37.2 grams of magnesium to produce magnesium nitride. Alright, now let's go to number 6. So now we need to know how many molecules of sulfur trioxide would react with 68.9 liters of water. So we see molecules. That means at some point we're going to need Avogadro's number. And we see liters here, so at some point we're going to need the molar volume. And this one turns out is already balanced. So we're going to start with what we know. We know we have 68.9 liters of water. And I guess we're going to assume that that's water vapor, because why else would we be using molar volume? But we need molar volume because we want to know how many moles of water we have. Okay, and then we need to go from moles of water to moles of sulfur trioxide. And so that's a 1-to-1, so for every 1 mole of sulfur trioxide, we got 1 mole of water. And that cancels. And now we need, let's see, we're trying to figure out how many molecules of sulfur trioxide. So we don't need the molar mass, we need Avogadro's number. So we get 6.022 times 10 to the 23rd molecules, per mole. And moles canceled. And we're going to get 1.85 times 10 to the 24th molecules of sulfur trioxide needed. Alright, so now let's go to number 7. Alright, on number 7, it wants to know the maximum number of grams of silver phosphate that can be produced when you react 287 grams of silver chlorate with 52.8 grams of sodium phosphate. Alright, so this one we are back to what we were doing before, where we have to do 2 separate calculations, because we want to know how many grams of silver phosphate we can get from 287 grams of silver chlorate, and we also want to know how many grams of silver phosphate we can get if we react all of 52.8 grams of sodium phosphate. So let's start with silver chlorate. So we have 287 grams of silver chlorate. Okay, and we need to go to moles of silver chlorate. So we need molar mass. And the molar mass is going to be 191.32. And so grams cancel out. And we need to go from moles of silver chlorate to moles of silver phosphate. And we know that for every 3 moles of silver chlorate from here, from the coefficient, we get 1 mole of silver phosphate. And so moles of silver chlorate cancel. And I'm leaving out a lot of these parentheses because they take up space and they're not necessary. Like, there's not multiple chlorates, there's not multiple phosphates, so I'm just going to go ahead and leave those out just to save space. And now we need the molar mass of the silver phosphate, which is 418.58 grams per mole. And that's going to cancel. And so it turns out we can get up to 209 grams of silver phosphate if we react all of our silver chlorate. Alright, so now if we react all, I did silver chlorate first, yeah. And so if we react all 52.8 grams of sodium phosphate, we need to know how many grams of silver phosphate we're going to get from that. And so we need the molar mass of the sodium phosphate, so we can figure out how many moles of that we have. Let's see. So for every 1 mole of sodium phosphate, that's going to be 163.97 grams. And grams cancel. And now we need the mole ratio. And I have painted myself into a corner. So let's see. We know that that's going to be a 1-to-1 ratio. So like every mole of the sodium phosphate that we use, we're going to get 1 mole of the silver phosphate. So let's save some space. And now we need the molar mass just like we used up here. And I'm going to save space and do things I wouldn't usually do because it's been a long day. Alright, so moles of sodium phosphate canceled, moles of silver phosphate canceled, and we can get 135 grams of silver phosphate. And since this is a lower number, this is how much the maximum number of grams that can be produced. Because it turns out that sodium phosphate is our limiting reactant. And that's all it's asking for in this problem. So now we can go to number 8. Alright, so I'm back. I had to pause and do a teleconference meeting for the district. And by the way, expect to be hearing from all of your teachers a lot more in the next little bit. But let's go on to number 8. So this one is asking, and I went ahead and marked stuff up in case you didn't notice, but so it's asking for how many formula units of iron 3 oxide that you can get if you react 108 grams of iron and 72.1 liters of oxygen. So once again, we got to figure out how much we can get if we react all of our iron and how much we can get if we react all of our oxygen. And as usual, the least amount is the most we can get. So first, we don't have a balanced equation, so we need to do that to start out with. And probably this one is a little bit tricky just because it has oxygen, and you know, oxygen always has to be a little bit difficult. But when you know here that we have 3 oxygens, so you can start out by doing 3 here, which means now you have 6. So double that. Now you have 6 here. You have 4 irons, so you need to have 4 over here, and it's not all that bad. So let's start with iron. So we know that we start with 100 grams of iron, and we need to go to moles of iron, so we need the molar mass. And the molar mass of iron is 55.85 grams per mole. And then those grams are going to cancel out. And then we need to go from moles of iron to moles of iron 3 oxide. So we need the mole ratio. And we know from our equation that for every mole of iron, or every 4 moles of iron that are produced, we get 2 moles of iron 3 oxide. So for every 4 moles of iron, we get 2 moles of iron 3 oxide. So now moles of iron cancel. Now we need to go from moles of iron 3 oxide to formula units. Watch out for that. It's not asking for grams, it's not asking for moles, it's asking for formula units. So we don't need molar mass, we need Avogadro's number. So since moles are on top, moles go on bottom over here, and we need 6.022 times 10 to the 23rd formula units. And now moles are going to cancel. And we have what we're looking for. So it turns out that you can get 5.82 times 10 to the 23rd formula units of iron 3 oxide if you react all 108 grams of iron that you have. First, we need to figure out how much we can get if we react all 72.1 liters of oxygen that we have. And since we have liters and we need to go from liters to moles, we're going to need molar volume, not molar mass, because molar mass depends on the identity, molar volume does not. We know that's 22.4 liters per mole. And so liters cancel out here. And we have moles of oxygen. We need to go to moles of iron 3 oxide. For that we need the mole ratio. And So we know that for every 3 moles of oxygen, we are going to get 2 moles of iron 3 oxide. So now moles of oxygen cancel. Switch pens. So now we need to go from moles of iron 3 oxide to formula units, and once again we need Avogadro's number. And I left off the Fe2O3 just for the sake of space. And so now we know that we can get 1.29 times 10 to the 24th formula units of iron 3 oxide if we react all 72.1 liters of oxygen. On this one, be careful. If you just glance at it, it looks like this is limiting because it's 1.29, but it's times to the 10 to the 24th. So you have like a lot more of this than you do of this. So the most iron 3 oxide that you can get from the amount of reactants given is 5.82 times 10 to the 23rd formula units, because this is your smaller number, so therefore iron's going to be your limiting reactant. These do get messy. Alright, let's go to number 9. We are almost done. Okay, so now we need to figure out how many moles of barium hydroxide you can get when you react 4.234 moles of barium and 8.902 moles of water. And this one is going to be another easy one, thank goodness. So let's see. So all we need for this one, since we're going from moles to moles, is a mole ratio. So we know that for every, let's see, this is balanced. So for every 1 mole of barium, we get 1 mole of barium hydroxide. My bad. And so you can get 4.234 moles of barium hydroxide if this is your limiting reagent, if you react all of this. Now, if you react all 8.902 moles of your water, you know that for every 2 moles of water, you get 1 mole of barium hydroxide. And you know that from the coefficients in your equation. And so moles of water cancel, and you know that you can get 4.451 moles of barium hydroxide if you react all of your water. This is the smaller number, not by much, but it's smaller. So your limiting reactant is the barium. And at the most, you can get 4.234 moles of barium hydroxide before you run out of barium. Alright, so last one. Let's go to number 10. Oh. And this is one of those big ones, but it's the last one, so it's not so bad. So it doesn't give us a balanced equation this time, but it wants to know the most or the maximum number of grams we can get when we react 67.8 grams of nickel. Oh my gosh, stop. And 37.3 grams of bromine. And it doesn't give you, well, it doesn't appear to give you a balanced equation, but if you look at it, it's already balanced. It's totally fine. So let's go ahead and start with nickel. See how much nickel bromide we can get if we react all the nickel we've got. So we're trying to go from grams of nickel. Oh my gosh. Why is it doing that? Okay, from grams of nickel to moles of nickel. And so we need the molar mass for that. And the molar mass of nickel is 58.69. And so now we need to go from moles of nickel to moles of nickel bromide, and that's a 1-to-1 ratio. And I'll put that on there since I've been lazy a couple times today. And now we need to go from moles of nickel bromide to grams of nickel bromide, so we need the molar mass for that. And that turns out to be 218.49 grams per mole. Okay, and so that if we type all that in, you can get moles of nickel bromide cancel. You can get 252 grams of nickel bromide if you react all of it. So now we need to figure out what we can get if we react all of our bromine gas. And so we know we have 37.3 grams. We need to figure out how many moles of bromine gas we have. And so the molar mass is going to be 159.80. And be careful with that. It's easy to just put the molar mass of the element bromine when it's one of these diatomics, but just make sure you double that for the molar mass. And again, we have a 1-to-1 ratio. So for every mole of nickel bromide, we need 1 mole of bromine gas. And I haven't been canceling. And then we need the molar mass of the nickel bromide again, which is the same as it was up here. So 218.49 grams of nickel bromide per mole. Cancel that out, and we can get 51.0 grams of nickel bromide. And so this is obviously going to be how much we get, because that's way lower. So the bromine gas is our limiting reactant. So this is part of our answer. So it wants to know how many grams of nickel bromide can be produced. It also wants to know which is our excess reactant and what mass of it is left over. So we need to figure out how much of the excess, or how much of this nickel that we used actually reacted, before we can figure out how much is left over. So another part of our answer, nickel is the excess reactant. Since that's part of your answer, we're going to put it in a square. And so to figure out how much of that nickel reacted, we're going to start with figuring out how much nickel we need to react with the exact amount of bromine that reacted, which was all of it. So let me get a different color. I like different colors. So let's start with the 37.3 grams of bromine that we started with and go to moles of bromine the same way we did before. Okay. And then from there, we need to use our mole ratio, which we know is 1-to-1. So for every 1 mole of bromine that reacted, you also had 1 mole of nickel react with it. And now we need to know the mass of the nickel that reacted. So we need the molar mass of the nickel, which is 58.69. Okay, and so if you calculate all that, it turned out that 13.7 grams of nickel reacted. But if we scoop back up, it wants to know how much is left over. So we need to subtract that from how much we started out with. So we know that we used 67.8 grams of nickel. Sorry, I'm using up all the space I got. And we need to subtract the 13.7 grams of nickel that reacted. And when we subtract that out, it turns out 54.1 grams of nickel was left over. And let's check to make sure we got all of our answers. So said what's the maximum amount that can be produced? That's 51 grams of nickel bromide. Which reactant is in excess? That's the nickel. And how much of it is left over? You got 54.1 grams left over. And I hope this was helpful. I don't expect anybody to have watched this whole entire video all the way to the end, but like I said before, I'll be sure to put in some timestamps for at least the beginning of each worksheet we went over. If not, each individual problem, I'll see what I have time for. But thank you guys for watching. Thank you for all your messages. Thank you for putting in all the work you have. And I really hope that I get to see you guys again before you graduate so that I can like blubber like a pitiful little baby at your graduation. But I'll talk to you guys soon. Thank you.